Hello everyone, this is video 12.1. We're going to be talking about areas of rectangles. Uh, this is the book refers to this as revisited. It is revisited if you've seen this before. If you've taken 137 before 138, then this would be revisited. If you are taking 138 first, I'm going to assume that you've done the area of a rectangle before, today. But the pedagogical tilt on the discussion of the area of a rectangle, you may not have seen or done or thought about to this point. So it's actually going to be the first thing we talk about on the first slide. So let's go ahead and get to it. Yeah, so chapter 4 covers a lot of what we're going to be talking about in this section. So this is the revisited part of what we're going to be revisiting here. So if you have taken 137, but maybe you've forgotten some of this material, or if you haven't taken 137, either way, it probably wouldn't be the worst use of your time to go back and look at chapter 4 and sort of refamiliarize yourself with the rectangular array model for multiplication. In chapter 4, we connected the area of a rectangle as a model for multiplication, and now we're kind of working that relationship backwards a little bit, looking at multiplication as a model for finding the area of a rectangle. So we need to have this understanding sort of in both directions. And if you haven't seen it, thought about it, worked with it, either in a long time or maybe even ever, it might be worth your time to go back and look over chapter 4. So what does it mean for a rectangle to have area? It seems like almost too basic of a question to even ask. We just sort of know what area means. It's the amount of surface that a bounded region has. Um, but a lot of students, if you ask them, what is the area of a rectangle, they'll just say length times width. Those give you the formula. And while that's true on a certain level, that's a very procedural answer to what is meant to be a very conceptual question. You're asking what does it mean, not how to find it. So, on a certain level, you need to be mindful of this type of misdirected answer. If a student asks you that question, to try to have a good answer for that. And it might be one that you really need to think about what it genuinely means. It may not be something that just comes off the top of your head or flows very naturally for you. So really think about what it means for a rectangle to have area. And then once we understand what the concept of area is, then we can get into how we calculate it, the procedural aspect of how we find that value. So one way that we can talk about the area of a rectangle is by putting little square tiles and covering it up. So you can think about like a kitchen or bathroom wall, putting little square tiles until we've covered up that entire area. And so each of those little squares has an area. It's one square unit, whatever that unit is. But we're covering up an area by smaller areas, and then we're counting how many of those unit smaller areas we have. So we have an example here, a 3 by 4 rectangle. We could put four squares across, and then four on top of that, and then four on top of that. And so now we've got the 3 by 4 completely tiled. And so then we would just go through and count uh, how many squares do we have. So here we'll draw it real quick. So here's my 3 by 4. And so we're just going to tile it like this. And so we're going to count each of these little squares right here until we find that we have 12 of these little squares. And so then the area here would be 12 centimeters squared, or 12 square centimeters, right? So this would be our area. So this is one way of thinking about it. You can probably see how this is only going to go so far. This works really, really well for rectangles, but it really only works really well for rectangles that have integer side values. So this is not going to work very well for triangles. It's not going to work very well for most parallelograms, trapezoids, rhombuses. It's a very limited approach. Now, that doesn't mean it's not worth doing, because it is very much worth doing in building the idea of what area is. That we're trying to cover the area of something, we're trying to cover a surface, we're trying to take up this region. So there is benefit to doing this, but we don't want to linger on it too long. Like it says right there, it's a starting point. That's it. So it's limited, but it is important. It is crucial because it helps build this concrete sense of what area is. So now we can move away from integer side lengths. And so this is the part where you probably need a little bit more chapter 4 than you did on the previous slide. Now we could do 4.5 by 6. And so here's my 6, and here's my 4.5. And there's a couple different ways we could think about doing this. So we could break this up into the 4 and the 1/2. And so now this 4 by 6 is just like the previous case. We know that this is going to be 24, this region here. And so this is just like the previous case, this integer values. But now what do we do with this 1/2 and this 6? So one way we could think about this is that we have 6 going across that are all 1/2. So this is 1/2, this is 1/2, this is 1/2, this is 1/2, so on and so on. And so we know that that's a unit, we know that's a unit, we know that's a unit. So you can see this is an intermediate approach to this, because while we have tiles that are not integer, they join together to make an integer value. These link together to make a unit. This makes a unit, this makes a 1, and this makes a 1 or a unit. So now we could count up 24 plus these 3 makes 27. So my area here would be 27 centimeters squared. Now, eventually, we're going to want to get to where we're just going to do 6 times 4.5. And so this is going to be my 24 plus 3 there, and get 27 this way. So eventually we're going to abstract this even further, moving a little bit further away, taking another step away from this concrete model. But again, the concrete model is important for helping establish what's going on and why we are able to do this procedural step. We don't want to just be doing multiplication because we're told to do multiplication. We want to be doing this multiplication because we can see how it makes sense. We can see how it works. So now we can get into a problem like this, where we have 2.5 by 3 1/3. And very similar to the previous problem, I'm going to break this into 3 1/3, 2.5. And so now I have this integer value here, so I know this is a 6. I've got 2 1/3. So again, I could break this into 1/3 and 1/3. I have 2 of these. So these make 2/3 together. I can break this into 3 1/2. So these 3 together will make 3/2 or 1.5. Now this piece is going to be a little bit harder to do because it's not going to create a unit piece like the halves. It's not an integer times a fraction, it's a fraction times a fraction. And so this again is something that you may want to go back and look at chapter 4. And I believe maybe there's another chapter that talks about multiplication with fractions, but I think it may all be in chapter 4. To get this, it's 1/6. And again, I'm not going to go back and talk more about that. If you know that it's 1/6, that's a good start. If you can explain why it's 1/6, that's even better. That's certainly where you want to be, especially if you've taken 137 already. So this is good review. If you haven't taken 137, hold on to that because you'll get to it when you take it. So for right now, we're just going to focus on the fact that this value is 1/6, knowing that there's a little bit more to this that needs to be explained. So now we can do all of these areas together. So this is going to be 6 plus 2/3 plus 1.5 plus 1/6. So putting everything in common denominators, this is 6, 4/6, 1 3/6, 1/6. So this makes 7 8/6, which is 8 2/6, or 8 1/3. Again, this is a very concrete, very intuitive way to do this area. Eventually, we're going to want to get to where we can do this just as the multiplication of these two numbers. And so we're just going to be multiplying 5 halves times 10 thirds and getting 56, which is going to make my 8 2/6, which is 8 1/3. So again, this is my abstracted version. This is so abstracted, I'm not sure why I'm doing it. And this is my concrete version. So this is my starting point, so students understand how and why the multiplication is applied, how it works, and then eventually moving into this abstracted form. Once we understand what this is connected to, what the conceptual foundation for this process is, then we can just do the abstraction and save ourselves some time. All right, so for your checkpoint, what is the area of a rectangle which measures 3 2/3 by 2 1/3? Again, we're not worried as much about the answer as we are the process and the explanation. So getting the answer is good. Being able to explain the how and the why of that answer, that's really what we're looking for. If you have any questions about this problem or any other problem from this section or from the video, as always, bring them to class and we'll get them answered. All right, thanks.